Welcome to Future Human Science, where we dive deep into the fascinating realms of technology and science. Today, we're embarking on an exciting journey into the world of fusion energy, a field often hailed as the holy grail of power generation. In this video, we'll explore the potential of fusion energy, how it works, its benefits, the current state of research, and the challenges that must be overcome to make it a reality. Let's start with the basics. What is fusion energy? Fusion is the process by which atomic nuclei combine to form a heavier nucleus, releasing a tremendous amount of energy in the process. It's the same reaction that powers the sun and other stars. Unlike nuclear fission, which splits heavy atomic nuclei to release energy, fusion merges light nuclei, such as hydrogen isotopes, to create energy. The allure of fusion energy lies in its potential to provide a nearly limitless and clean source of power. Fusion uses isotopes of hydrogen, such as deuterium and tritium, as fuel. Deuterium can be extracted from water, and tritium can be bred from lithium. These resources are widely available, making fusion fuel both abundant and sustainable. Fusion does not produce greenhouse gases or long-lived radioactive waste like fission does. The byproducts of fusion reactions are generally less harmful and have a shorter half-life, which significantly reduces the environmental impact. Fusion reactions release energy on a much larger scale compared to chemical reactions or even nuclear fission. The energy density of fusion is so high that a small amount of fuel can produce a large amount of power. Fusion reactions require extremely high temperatures and pressures to sustain. These conditions include temperatures of millions of degrees Celsius to overcome the electrostatic repulsion between positively charged nuclei. This is much hotter than the core of the sun. To achieve fusion, the fuel must be compressed to extremely high pressures to ensure that the nuclei are close enough to overcome their mutual repulsion and collide. The fuel must be confined long enough for the fusion reactions to occur. There are two main approaches to confinement: magnetic confinement and inertial confinement. Magnetic confinement uses powerful magnetic fields to contain a hot plasma of fusion fuel. The most well-known magnetic confinement device is the tokamak. The ITER, International Thermonuclear Experimental Reactor, project in France is a major international effort to build a tokamak capable of producing more energy than it consumes. Inertial confinement uses lasers or other forms of energy to compress a small pellet of fusion fuel to extremely high pressures. The National Ignition Facility, NIF, in the United States is a leading facility in this area, using high-powered lasers to achieve the necessary conditions for fusion. Despite its potential, achieving practical and sustained fusion energy has proven to be extremely challenging. Maintaining the necessary temperatures and pressures for fusion reactions is a significant engineering challenge. The plasma must be kept stable and isolated from the walls of the containment vessel to prevent energy losses and damage. Current fusion experiments require more energy to sustain the reaction than the energy produced. The goal is to achieve a net positive energy output, where the energy produced by the fusion reactions exceeds the energy input required to sustain the reaction. The materials used in fusion reactors must withstand extreme temperatures, radiation, and mechanical stresses. Developing materials that can endure these conditions and maintain their integrity over long periods is crucial for the success of fusion power. The cost of developing and building fusion reactors is currently very high. To become commercially viable, fusion energy needs to achieve a level of cost-effectiveness comparable to or better than other energy sources. Despite these challenges, progress in fusion research continues to advance. The ITER project, which aims to demonstrate a sustained fusion reaction, is a significant step forward. ITER is designed to produce more energy than it consumes and serve as a test bed for future fusion reactors. Several private companies and research institutions are exploring alternative approaches to fusion energy. These efforts include developing new reactor designs, improving plasma confinement techniques, and exploring different fuel cycles. The potential benefits of fusion energy are immense. If we can overcome the technical and economic challenges, fusion could provide a nearly limitless source of clean, safe, and sustainable power. It could play a crucial role in addressing global energy needs and mitigating climate change by reducing our reliance on fossil fuels. In conclusion, fusion energy represents one of the most promising frontiers in power generation. Its potential to provide abundant, clean, and safe energy makes it a key focus of scientific research and technological development. While significant challenges remain, the ongoing advancements in fusion research bring us closer to realizing this transformative energy source. Thank you for joining us on this exploration of fusion energy. If you found this video insightful and want to stay updated on the latest advancements in technology and science, be sure to like, subscribe, and hit the bell icon so you never miss an update from future human science. Until next time, stay curious and keep exploring the exciting world of technology and science with us.